若华牧师分享到，启示录早在2000年前已经预言，当世界踏进最后7年后3年半，就是世界最后的1260天里面，世界会进入大灾难时期。而这一场大灾难将会是全球性的，意思是世界将不会有任何所谓的安全区域，只要是活在地球上的人类都会被这场灾难牵连。透过过去12年间若华牧师所分享的极具前瞻性的2012信息，让我们得知这场1260天大灾难的成因是 X 行星的重临。有关 X 行星会为地球带来的灾难，其实圣经早已记载。第一次是创世纪的挪亚大洪水，第二次则是出埃及记，发生在古埃及的石灾。在8年前，若华牧师也曾在2012信息之 X 行星分享古埃及人曾以他们的角度去记载这一场石灾，按他们亲眼所见，石灾不但发生在埃及，而是发生在全世界，并且这一场普世的灾难是由一颗巨大的行星逼近地球所导致。现在我们已经知道，这一颗巨大行星是近100年天文学家不断寻找其踪迹的 X 行星。当时若华牧师已经分享，当 X 行星逼近地球，其轨迹与地球和太阳连成一直线的话，会令太阳爆发极为巨大的太阳风打向地球，就是延续着 Adams 所说的 Q-Salt。而另一方面，当 X 行星逼近地球，其巨大引力也会带来大量的陨石，当中只要部分陨石击中地球，都会为地球带来灾难。事实上，这种有陨石袭击所留下的痕迹，其实我们几乎每天都能看见。因为当我们望向月球的时候，单凭肉眼也可以看见月球表面并不平整，有着大小不同的凹痕，这些其实正是由陨石撞击月球表面所引致。甚至不用追溯很远的历史，近代在27年前的1994年发生了舒梅克里维9号彗星撞击木星的事件，使人类亲眼见证了陨石撞击的可怕。舒梅克里维9号彗星临时编号 D1993F2， 又译作舒梅克里维9号彗星或者舒梅克里维9。这颗彗星在1994年7月中下旬与木星相撞，这是人类首次直接观测到太阳系的天体撞击事件，引起全球多间主流媒体关注，以及引发各地天文学家和天文爱好者观测热潮。人们通过这次事件更加了解木星和它大气的资料，以及木星在太阳系内以强大引力扮演着清理太空垃圾的清道夫角色，使地球上的复杂的生命免受频繁的天体撞击影响。这颗彗星是由美国天文学家尤金·卡罗琳·舒梅克夫妇和天文爱好者大卫·李维，在1993年3月24日，在美国加州帕洛马天文台共同发现，是他们发现的第9颗彗星，因此根据国际星体命名规则，依照他们的姓氏命名。这彗星很可能源于火星和木星轨道之间的小行星带，随后成了周期彗星。电脑推算运行轨道的结果显示，出自1994年7月8日，在距离木星表面4万公里的时候，因受到强大引力影响而分裂为21个小碎块，并在刚离至标准时间1994年7月16日20点15分开始，以每小时21万公里的速度陆续坠入木星大气层，撞向木星的南半球，形成了彗星撞木星的天文奇观。在众多碎片里面，以碎片 G 的撞击威力最大，在7月18日7点32分撞向木星，威力达6兆吨 TNT 炸药，其当量相当于全球核武器储备总和的750倍，造成一条比地球直径还要长的疤痕。
The lasting impacts of comet Shoemaker-Levy 9. At the close of the last century, a comet captured into orbit around a planet traveled too close and was shredded by its gravity into multiple pieces, some as large as half a mile or 1 kilometer long. Those fragments would plunge into the planet's atmosphere in a series of impacts. Would the impacts be spectacular, or would the comet fragments disappear without a trace? In July 1994, astronomers around the world watched with bated breath as the fragments of comet Shoemaker-Levy 9 slammed into the planet Jupiter. Dr. Kelly Fast was one of the impact's observers and is now manager of NASA's Near-Earth Object Observations program.
It was just incredible to watch. Such an impact event had never before been witnessed, let alone studied. Ground-based telescopes around the world and spacecraft like NASA's Hubble Space Telescope and even the Galileo orbiter en route to Jupiter were used to observe the impacts. The discovery of the comet by Carolyn and Gene Shoemaker and David Levy gave us about a year to plan our observations.
The impacts proved to be impressive. The fragments, some 21 in all, plunged into Jupiter's atmosphere over the course of 6 days. At impact, they were traveling at a speed of about 37 miles per second, or 60 kilometers per second, heating the atmosphere to at least 53,000 degrees Fahrenheit, or 30,000 degrees Celsius. Like the splash from throwing a rock into a pond, the impacts created giant plumes of material from Jupiter's lower atmosphere, which rose as high as 1,900 miles, or 3,000 kilometers above the cloud tops into the stratosphere. In the aftermath, the plume splashback scarred Jupiter's atmosphere with dark clouds of impact debris, which could be seen for months as they were gradually dispersed by Jupiter's winds.
不但月球和木星会受到巨大陨石的袭击，其实地球也曾多次受陨石袭击，并带来可怕的灾难。例如，很多研究恐龙的科学家都认为，地球上的恐龙之所以被灭绝，是因为6500万年前有一颗巨大陨石击中地球，令地球气候和环境突变，最终令所有恐龙绝种。陨石击中地球而产生巨大灾难的事件，更不止出现一次。地球曾多次受巨大陨石侵袭，每一次也会在地表上留下陨石坑，成为一个证据，证明地球曾多次受陨石袭击。例如，地球上最明显、最为人熟知的陨石坑，是位于美国亚利桑那州北部沙漠里面的巴林节陨石坑。据推测，形成巴林节陨石坑的陨石是一颗直径约50公尺的裂铁质陨石，其撞击速度至少达每秒数公里。撞击所释放的能量相当于10兆吨黄色炸药。更加惊奇的是，2013年2月15日，切里亚宾斯克小行星撞击事件在俄罗斯乌拉尔联邦管区的切里亚宾斯克市一次小行星撞击事件。当天约上午9点15分，陨石进入大气层的时候，直径约15米，质量约7000公吨，在天空中留下约10公里长的轨迹。主要碎片击中了切巴尔括湖，事件中造成1491人受伤。
On February 15th, 2013, over Chelyabinsk, Russia, an asteroid heavier than the Eiffel Tower slammed into the atmosphere. And then, 30 kilometers above the ground, it exploded. This violent event was brighter than the sun, but so high up that it was silent for a full 90 seconds after the blast, which only made the devastation worse.
So you see all these videos of people, look at what was that? They see the smoke trail in the sky, and oh, that's amazing. And then, just when you think nothing's going to happen, the shockwave hits and it blows out the windows. 1,000 people got glass in their face, in their eyes, because they're looking through the windows.
The shockwave damaged thousands of buildings and injured 1,500 people. What makes the Chelyabinsk incident kind of embarrassing is that the very same day, scientists had predicted that an asteroid would make a close flyby of Earth. And they were right. 16 hours after Chelyabinsk, a similar-sized asteroid, known as Duende, came within 27,000 kilometers of Earth's surface. That's closer than satellites in geosynchronous orbit. But while they correctly predicted this close approach, they completely missed the unrelated asteroid that exploded over Russia. And the truth is, this happens all the time. We're really not that good at detecting asteroids before they hit us. Since 1988, over 1,200 asteroids bigger than a meter have collided with the Earth. And of those, we detected only 5 before they hit, never with more than a day of warning. With all our technology and all the telescopes across the Earth, not to mention the ones in space, why do we struggle to detect dangerous asteroids before they strike? What are the chances that a big asteroid will hit, wiping out most, if not all, life on Earth? And if we saw one coming, what could we do about it? Asteroids are the leftover debris from when our solar system formed. 4.5 billion years ago, rocks and dust clumped together into molten protoplanets. Inside, heavy elements, metals like iron, nickel, and iridium, sank into the core, leaving lighter silicate minerals on the surface. Some of these protoplanets grew into the planets we know today, but many more collided with each other, breaking into pieces. These pieces continued orbiting the sun and smashing into each other and breaking into even smaller fragments. These became the asteroids, which is why some of them are rocky, loose conglomerates of gravel-sized rocks called rubble piles, and others, from the cores of planetesimals, are mostly metal.
So this is an iron meteorite, and essentially it's the piece of a core of a small planetary body, like it's basically a small planet, that formed 4.5 billion years ago, differentiated, so the core material fell out, and then this thing was smashed apart by a collision with another asteroid. That's the oldest thing you'll ever see.
Most of the asteroids have stable orbits between Mars and Jupiter in the main asteroid belt, but some have made their way closer to Earth, and these are known as near-Earth objects. They are of greatest interest to us because of the threat they pose. In his last book, Stephen Hawking considered an asteroid impact to be the greatest threat to life on Earth. But finding asteroids is difficult for several reasons. Most are spotted by ground-based telescopes.
So what you do is you take a sequence of pictures, 1, 2, 3, 1, 2, 3, 4, and you look for essentially a moving dot. And it's moving because it's orbiting around the sun, whereas the stuff far away, the stars and galaxies, are not.
But you have to look carefully. Asteroids are not very big. They range from meters up to kilometers in size. And in the vast expanse of space, rocks like that just don't stand out. And even the small ones can be damaging. The Chelyabinsk meteor was only around 20 meters in diameter, roughly the width of 2 school buses. Plus, asteroids are rough and dark. They only reflect around 15% of the light that hits them. So our best chance to see them is when they're fully illuminated by the sun. And that's why over 85% of the near-Earth asteroids we've detected were found in the 45 degrees of sky directly opposite the sun. This is called the opposition effect, and it means there are likely more near-Earth and potentially hazardous asteroids that haven't been detected yet. Any asteroid approaching from the direction of the sun just can't be seen. This is exactly what happened with Chelyabinsk. So far, we have detected and cataloged 1 million asteroids, the vast majority of which are in the main asteroid belt. But 24,000 are near-Earth objects, ones that we need to keep a particularly close eye on, because even once you've detected an asteroid, it's hard to tell if it will hit the Earth.
So if you just discover an object and you only have data from a few days, then you can't really tell where it's going to go because you're trying to take this little arc of motion and predict it far into the future. So what you need is observations over years and years. But even if you have perfect observations of an asteroid, there's kind of a fundamental limit to how far in the future you can predict. And that's because a couple of effects. But one is that, they're not just orbiting the sun with no other influence. All of the planets have gravity, and all of the planets are pulling on near-Earth asteroids and can change the orbit significantly. So there is something called dynamical chaos, which basically means after a certain amount of time, you don't know where the asteroid is going to be. And in practice, what that means is we can't do any work more than 100 years in the future. So the maximum time you can predict with any accuracy at all where a body will be is about 100 years.
And this is pretty important, because we know with certainty if one does hit, the results will be dramatic. This is Barringer Crater in Arizona. It's named after mining engineer Daniel Barringer, who was the first to suggest it was formed by a meteorite impact. The prevailing view, even up until the 1950s, was that it was created by volcanic activity. But Barringer was convinced it was the site of an iron meteorite impact. So in 1903, he staked a mining claim and began drilling for the metallic meteorite, which he believed to be worth more than $1 billion 1903 dollars.
Yeah, so people are motivated by money, right? So they thought, hey, we can get some iron for free, basically. So they started to drill in the bottom of the crater and found nothing. And then they started to do other exploratory drills, and this went on for years and decades. They started to drill sideways. Somebody said, maybe it came in from an angle, which it did, and maybe the iron is not under the middle, but maybe it's over there under the wall. So he was doing drilling. If you go there, you can see the drills now. He was drilling around the wall, he found nothing. So what they didn't realize is when you have an impact at high speed, it's not like you're throwing a stone into a brick wall, and it makes a hole and sticks in there, or just bounces off. It's explosive. It's like totally explosive. So the kinetic energy of the projectile comes in maybe 30 kilometers per second. The kinetic energy of the projectile is big enough to completely vaporize the projectile. It turns it into a gas. And that gas is super hot and super high pressure. And it explodes, and it blows out the crater. So the projectile doesn't really exist after the impact. Little pieces can survive. But this 50-meter body was basically obliterated. So he was looking for something that did not exist.
He spent 27 years mining the crater, drilling down to a depth of over 400 meters. But what he was searching for had vaporized on impact 50,000 years earlier. The 50-meter asteroid, not that much bigger than Chelyabinsk, released the energy equivalent of 10 megatons of TNT. That's over 600 times the energy of the Hiroshima bomb. So the thing that most closely resembles a meteorite impact is a very large nuclear explosion.
This is the actual size of the T-Rex skull. And I thought, this is such a cool thing, I gotta have it. So I bought the T-Rex. The dinosaurs were wiped out by a 10-kilometer sized asteroid that hit about 65 million years ago. So above a critical size, which is probably a couple of kilometers, an impactor delivers so much energy that it has a global effect. So essentially, it launches a whole bunch of debris into suborbital trajectories. So the ejector goes around the Earth, falls back into the Earth, all over, even on the other side of the planet from where the impact occurred. And what that means is the whole sky lights up with wall-to-wall meteors. So you can imagine the sky turning from, a nice blue day like today into essentially a red-hot glow, like being inside a toaster oven. So the first effect of this impact, apart from the initial blast near where the actual impact occurred, the first effect is the sky turns into a great source of heat, and it cooks everything on the ground. So these guys were basically cooked.
Cooked alive.
Cooked alive as they were walking around. The only animals that had a chance were the ones living in tunnels under the ground, or maybe in the water. And they were able to come back and take over without having to deal with the dinosaurs as a major obstacle.
What are our chances that Earth gets hit by another 10-kilometer or bigger asteroid?
In your lifetime, assuming you live to be 100 years old, you have a 10-kilometer impactor like the KT extinction event every 100 million years or something like that. So the probability of getting it in 1 year is 1 in 100 million. So you have 1 in a million chance of dying from a 10-kilometer impactor. But because we know that there are no 10-kilometer impactors with a path that intersects the Earth for the next 100 years, your chance of dying from that is actually 0. So work done already has reduced that down, from 1 in a million to nothing.
So the good news is there won't be another dinosaur-style extinction event in our lifetimes. But there are exponentially more asteroids of smaller sizes. For every 10-kilometer asteroid, there are roughly 1,000 1-kilometer asteroids, and they're still capable of doing a lot of damage.
1 or 2 kilometers is capable of causing local but massive damage. So that means, you know, instead of wiping out the entire world, you would wipe out the equivalent of some European country, like France or Germany, to mention 2 of my favorites. So you would obliterate those countries with the impact of a 1 or 2 kilometer sized body.
Do we know about all the 1 to 2 kilometer bodies that could hit us?
We think that we know 90-something%, maybe 98% of those bodies have been identified, and we have their orbits, and we can make reasonable predictions for the next 10 years or something about where they'll be. And we seem to be okay at the moment. But, you know, what about the ones that are just a little bit less than a kilometer? What about the ones that are 800 meters? That's still pretty savage if it hits.
And this is possibly where the greatest threat of asteroids remains. A few hundred meters is large enough to obliterate a large city, but small enough that we haven't detected them all yet.
We're missing a lot of 100-meter-sized projectiles, and those guys are big enough to cause substantial damage on the Earth, depending on where they hit.
So it could destroy a city?
Yeah, it would knock down the buildings in the city, it would cause citywide fire, and if it hit the ground, it would throw up ejecta that would come back down and rain on the ground. It would be high-speed ejecta that would obliterate a 100-kilometer zone around it.
And this could happen tomorrow?
Well, it could, yeah.
If we saw a big one coming, what's our best bet for, I mean, could we do anything about it? What would we do about it? Is there anything we can do to actively...
No, there's nothing we can do. I was on a committee that looked at that, okay, like 10 years ago. Like, what could we do? One option would be to try to bomb it. It's the standard thing. We don't know how that would work out. Even when you got it there, and even if you could explode it on the surface or in the surface, it's not clear what you would do, because typically what happens is you blow up a body and the fragments move out, they expand out, but not very quickly, and then gravity pulls them back together again. So it would reform as a rubble pile if it was not already a rubble pile to begin with, which it probably would be because of past impacts. So blowing up a rubble pile is something that we don't really know about. Another idea is you could be all gentle and attach a rocket to the asteroid and just try to push it aside. Let's nudge it aside. Instead of trying to blow it up, let's just push it gently aside so that it deflects it and it doesn't hit the Earth. The trouble is, when you work out the numbers, none of the rockets that we have can push it around enough. You would have to keep the rockets attached to the surface, which we don't know how to do. Remember, it's a rotating body for centuries to have a significant effect on the motion of the asteroid. So forget bombs, forget attaching rockets. Ablating the surface, basically you boil the surface with a laser. We don't have any lasers powerful enough and probably can't make lasers powerful enough to do that from the Earth. We would have to take the lasers to the object, which is even more difficult. The idea that you could wrap an asteroid in cooking foil, aluminum cooking foil, is another nice one. It may be a good one, the best one, but it still doesn't really work because we don't know how to do that. We don't have a way to launch enough cooking foil to wrap up an asteroid and change its radiative properties, which would itself move the asteroid around. So the truth is, to be honest, we do not have a way now to deflect a kilometer-sized asteroid at all.
That could destroy a country.
Yeah, we just don't have a way.
And 10 kilometers?
10 kilometers is absolutely 1,000 times more hopeless. So when we discussed this, you know, we had all these grand ideas. Oh, we could do this, and none of them worked. We came down to the most basic idea. Well, maybe if we could figure out where the asteroid is going to hit, like which city is it going to explode over, we can evacuate that city. And then we looked at the history of city evacuations, and we looked at cases, you know, where, for example, you have like a week's warning where some hurricane system is going to come in and flood a city. And evacuation just doesn't work either. And the reason is very, very simple. Like going into a city, there are not that many freeways. If you have millions of people trying to get on a freeway, the first time a car breaks down, you block that freeway. So instantly you have millions of people trying to get out of the target zone, and they won't be able to because all of the roads will be instantly blocked. So again, even evacuation of a city is probably the most hopeful thing that we could try to do. Even that's really, really difficult because of the large numbers of people involved. What I think all reasonable people would conclude is, let's do the thing that we can do first. So let's look for them. Let's do the surveys. Let's build the telescopes. Let's put this telescope in space. That will be a major contribution to understanding the threat from the asteroids. And then, when we find a particular object that looks especially dangerous, then we can focus on it. We can focus everything we have on it. And we can begin to think seriously and with real motivation about ways to deflect it.
这正如启示录所预言，在大灾难最后的1260天，地球至少将会受到2次巨大陨石袭击。而这2次陨石袭击极可能正如上述影片所讲到，大小约1公里甚至更大型的陨石，直接击中地球的陆地和海洋，引起巨灾。启示录8章5到11节，天使拿着香炉，盛满了坛上的火，倒在地上，随有雷横、大声、闪电、地震，拿着7支号的7位天使就预备要吹。第1位天使吹号，就有豹子与火掺着血掉在地上，地的1/3和树的1/3被烧了，一切的青草也被烧了。第2位天使吹号，就仿佛火烧的大山扔在海中，海的1/3变成血，海中的活物死了1/3，全肢也坏了1/3。第3位天使吹号，就有烧的大星，好像火把从天上落下来，落在干涸的1/3和重水的泉源上。这星名叫阴沉，重水的1/3变为阴沉，因水变苦，就死了许多人。